Okay, let's start our class. Okay, so today we're going to talk about the last parts of the unit 3, and only we're going to talk about the 3 major topic, but only just one. The first topic is the most important parts. Okay, for the rest 2, we do have one question for the for those 2 topic, but not that important. Okay, yeah. So first of all, let's just review what we learned last time. Last time we talked about the ideal gas law, okay? And we talked about what is the STP. You remember what is STP? That's a standard temperature and pressure, okay? The standard temperature and pressure, which means you know what is the temperature and what is the pressure. Standard STP, that means the temperature is at 0 Celsius or 273 Kelvin. So that is the temperature for standard STP. The pressure will be 1 atmosphere. Okay, so this is the STP condition. And we also talk about what is called the molar volume, which means if we have a 1 mole of the gases, what exactly the volume of these gases at STP condition. And we call this is a 22.4 liter per 1 mole of the gases at STP condition. So if we know the temperature is 273 Kelvin, pressure is 1 atmosphere, and we have 1 mole of gases, the volume of this gas should be 22.4. Because when we talk about ideal gas law, we know the PV equal to nRT. And if you have the P is 1 atmosphere, volume, the moles of gas is 1 mole, and the temperature is 273 K. And we know the ideal gas constant, the volume should be a fixed number. And the fixed number is 22.4 liter. Okay, yeah, so that is why, based on the ideal gas law, if the 3 parameters are fixed, the 4th one will also be fixed. Okay, yeah, so that is why we can just based on the P, V, and T is dynamically related to each other's. But if we have a certain number for 3 of those parameters, the last one will be also the fixed number. Okay, so this is what we talk about based on the ideal gas law. And we also talk about the constant. Ideal gas constant has a lot of different number, but the only difference is unit. If you're using different unit, you're going to have the different constant number. Okay, yeah, so the number we're using is 0.08206. And this is a liter atmosphere divided by Kelvin divided by mole. So that is why the volume should be in liter, atmosphere should be the pressure, Kelvin should be for temperature, and mole is for the moles of a gas. Okay, yeah, if you're using those units, then you should be able to using the 0.08206. And once again, this number will not be given in the exam. So you better put that into the cheat sheet. And by the way, the unit 3 is allowed, you're still allowed to have the cheat sheet, the half-page cheat sheet, but for the final, you're not allowed. Okay, final only just having what exact shows in the exam. The exam will give you the periodic table and some constant. Okay, yeah, but not for the cheat sheet. I mean, you cannot use the cheat sheet for the final. Okay, yeah. Okay, for this is the ideal gas law, and we talk about there's another variation for the ideal gas law. The variation is the pressure time the molar mass of the gas. That should be equal to mass of the gas over the volume and the time R time T. Or you can write the mass over volume, that's the density. You can also write, which is the density of the gas time R and time T. Okay, so That is another variation for the ideal gas law, okay? Yeah, so that's really depends on what the question asking for. Then you can base on the question and to figure out what is the equation you're going to use. Okay, yeah, today we're going to continue talk about ideal gas law. I mean, we're going to using the ideal gas law in the stoichiometry, okay, yeah. So which is called a gas stoichiometry. Okay, I want you to remind yourself what exactly is stoichiometry. In the last lab, we did one of the stoichiometry. Sorry, I need to pull this out. So last time in the lab, we did another stoichiometry. It's called solution stoichiometry, right? I mean, that's for the titration. Okay, we based on the concentration of the KHP solutions, and then we figure out what is the moles of the KHP solution, and based on the stoichiometry, we figure out how many moles of the sodium hydroxide that we use, and then we can figure out what is the concentration of the sodium hydroxide, right? So this is what we talk about, and we did 2 practice in the study guide, okay, for the solution stoichiometry. So in general, stoichiometry is just, for example, we have the A plus 2B and to form 3C. And based on, if we know the moles of the A, and then we can base on the coefficient to figure out the moles of the B. So this is what we call the stoichiometry, okay? So moles of something to figure out most of other things in the chemical equation, that is called stoichiometry. But we have a different way to figure out the moles of the stuff, because the ratio over here is used in those ratio is for mole ratio. It's not for mass. It's not for concentration. It's not for volume. Okay, it's for mole. So the way to figure out mole is different, right? If we're using the mass to mole, mole to mass stoichiometry, if I give you the mole mass, well, you know, we're gonna convert the mass to the mole. By using mass over molar mass, you got a mole, and then use a mole to do the stoichiometry. Solution stoichiometry is the same thing. Okay, solution stoichiometry is just using molarity and the time volume to figure out the mole, right? Yeah, but right now, today, we're going to talk about another stoichiometry, which is called the gas stoichiometry. Well, think about how do we got the mole of the gas? Well, PV equal to nRT. Remember, what is N? N is the moles of a gas, okay? So again, this is another way to figure out the moles of a gas, to mole in the compound, in the chemical reaction, which is using the ideal gas law, okay? So this is another variation to find a mole of the reactant or the product. That makes sense, right? Yeah, so that is why this one is called the gas stoichiometry, because if you want to find the mole of a gas, you have to using the stoichiometry, you have to using the ideal gas law to find the moles of a gas. That's it. This is another way, okay? Yeah, so let's work on this. Yeah, let's work on the first question, okay? The first question said, what volume, and this is, I think this is in the page 19. Page 19 in your green study guide. Okay, so let's say, what volume of oxygen is produced when 28.5 grams of the hydrogen peroxide decomposed to form water and oxygen at 150 Celsius and 2.0 atmosphere. Okay, well, then let's let's work on this. First of all, we need to set up the equation, right? Without the equation, then you cannot solve anything. Let's see. This one, we're having the hydrogen peroxide, and this hydrogen peroxide is a liquid hydrogen peroxide. It's going to decompose to water and oxygen. So they got decomposed to water and plus oxygen gases. Okay, then you're gonna balance this equation. So we gotta, this should be 2 over here, okay? And then we have 1. Okay, then this is the equation. The equation telling us 2 moles of the hydrogen peroxide can decompose to 2 moles of water and 1 mole of oxygen. Okay, so let's think about what we have. Okay, the question we have a 28.5 gram of the hydrogen peroxide. Okay, and then they're asking for what is the volume. Okay, what is the volume of the oxygen? But they also give us some of the condition like a temperature. The temperature is 150 Celsius. Again, you're going to plus 273 to get the Kelvin, and that's going to be 423 Kelvin. So that is the temperature. And we also know the pressure. The pressure here is 2.0 atmosphere. Okay, and also okay, the question asking for volume, and based on the equation PV equal to nRT. So we know the pressure, and we know the temperature. And if we got the moles of a gas, then we should be able to figure out the volume, right? So that is why the key is how to find the moles of a gas, moles of the oxygen. Well, obviously, you know the moles, the mass of the hydrogen peroxide. So you're gonna figure out what is the moles of the hydrogen peroxide. And based on the moles of hydrogen peroxide and based on 2-to-1 ratio, and you should be able to figure out the moles of the oxygen, right? So you based on the stoichiometry, figure out the moles of oxygen, and the moles of oxygen will be used in the ideal gas law, and then you can figure out the volume of the gases. That makes sense, right? So this is one way. First, we based on the stoichiometry, figure out the moles of gases, and then using the ideal gas law to figure out the volume or pressure or something else. Okay, so this is one way, and let's just work on this. Okay, yeah, well, so first, let's just try to figure out what is the moles of a gas. It's just 2 steps, right? So first, you have a 28.5 gram of the hydrogen peroxide, and then you're going to convert that to the moles of the hydrogen peroxide by divided by the molar mass. So the molar mass of the hydrogen peroxide, and you can see molar mass of hydrogen peroxide is 1 times 2 plus 16 times 2. So 2 plus 32, we got 34 gram per mole. So that is the molar mass of the hydrogen peroxide. Then you can, okay, so that much of the hydrogen peroxide and divided by the molar mass. Once again, a lot of people confused. When you're divided by molar mass, you shouldn't involve the 2 of that. This 2 means the 2 coefficient over here is only being used for figure out the moles of the oxygen for the stoichiometry, not for divided by the molar mass, right? The molar mass is 34 gram per mole, which means 1 mole of the hydrogen peroxide is 34 gram. The 34 gram per hydrogen peroxide is 1 mole. If you're time 2, then what are you gonna? If you're time 2 moles, then what happened? Your right is 2 moles of the hydrogen peroxide is 34 gram. It's not, right? So when you write this, you should divide by the 1 mole of the hydrogen peroxide is that much. Well, if you want the time to write 2 moles of the hydrogen peroxide, you can, but you need to double the molar mass, right? 2 moles of the hydrogen peroxide should be 68 grams. It makes sense, right? So this is just divided by molar mass. You can get a mole of the hydrogen peroxide. So you divide by canceled. Now you got the moles of hydrogen peroxide. Then you based on the stoichiometry. You see, the stoichiometry is used over here. Once you figure out moles of this, then you figure out how to convert the moles of the hydrogen peroxide to the moles of the oxygen. So obviously, 2 moles of the hydrogen peroxide will form 1 mole of the gases, oxygen gases. This is coming from the chemical equations. The 2 is applied over here. 2 moles of the water, hydrogen peroxide, form 1 mole of water, oxygen. So this and this is canceled. Now you got moles of oxygen. Okay. Now you can, based on this, to figure out the moles of oxygen. Again, you gotta make sure you have a parenthesis to cover the bottom parts. So 28.5 times 1 divided by parenthesis 34 times 2 parenthesis, and you got a 0.419. Okay, you have 0.419 mole, and this is a mole of the oxygen. So once you figure out the moles of oxygen, then we can, based on the PV equal to nRT, to figure out the volume of the oxygen, because we know the mole. You see, in this equation, we know the mole is 0.419 moles of the oxygen. We know the mole, we know the pressure, we know the temperature. We should be able to figure out the volume. Okay, so the volume, based on the ideal gas law, the volume will be just equal to nRT and divided by the pressure. The volume equal to nRT divided by pressure. So the volume, that's N, that's just a 0.419 times R, which is 0.08206, and time the temperature is 423 Kelvin divided by pressure. The pressure is 2.0 atmosphere. So now you put those into your calculator, and you should be able to figure out the volume of the oxygen. 0.419 times 0.08206 times 423 divided by 2. The answer will be 7.27. 7.27, and this is in liter. Well, but if you look at the numbers over here, I think we need to keep 2 sig instead of 3. So the answer should be just a 7.3 liter. Okay, 7.3 liter. Okay, so you see, this is one kind of the stoichiometry. You based on the stoichiometry to figure out moles of gas, and then based on the ideal gas to figure out either the volume or pressure or temperature for this kind of the gases. Okay, but most of the case they try to figure out the volume. Okay, most of the case they try to figure out volume. Okay, and then obviously you can also go backwards, which means you first, based on the ideal gas law, to figure out the moles of a gas, and then use the moles of a gas in the stoichiometry. Okay, and this is what happened for the second question. Okay, this is what happened for the second question. So let's work on the second question. Since this practice, we have 5 of the gas stoichiometry. Just to let you know, 1 of them will be applied in the exam. Okay, well, obviously the number will change a little bit, but 1 of them will apply in the exam. Okay, so let's see question number 2. The following reaction forms 6.41 liter of the oxygen at the temperature 18.7 Celsius, and the pressure that much torr. So what mass of the potassium chlorate must be decomposed? Okay, so this one for you is hard because I mean you don't know what is the chemical equations. Okay, so let me just write down what is chemical equations. They have the potassium chlorate, and the potassium chlorate is decomposed to form potassium chloride and the oxygen. Okay, so when you're set up this equation, this is gas. Put a 2 over here, 2 over here, and 3 over here. And this equation is done. Okay, so it's balanced. So now we have this equation. Obviously, this equation talk about 2 moles of the potassium chlorate will form 3 moles of oxygen. So now what we have, we know the volume of the oxygen is 6.41 liter, and the temperature is 18.7 Celsius, and the pressure is 731 torr. And then you see, we know the volume, we know the temperature, we know the pressure based on the PV equal to nRT. Then we know the pressure, we know volume, we know the temperature, so we should be able to figure out the moles of the oxygen, right? Based on those 3 parameters, we should be able to figure out the moles of oxygen. But before we're doing this, remember what we're gonna do first. Convert the numbers, okay? Yeah, because we need to use the correct unit. For the volume, yes, liter should be fine. Temperature should be in Kelvin. So you're gonna plus 273. And you got 0.7 plus 273, you got 291.7. This is Kelvin. And then torr also need to be converted to atmosphere. And we know 760 torr equal to 1 atmosphere. So your time 760 torr equal to 1 atmosphere. Then you can convert that to the atmosphere. 731 divided by 760, you got 0.9618. 0.9618, and this is in atmosphere. Okay, so now we got the unit that we required, and then we can base on this to figure out the moles of gas. And then what happened? If you know the moles of the oxygen in this equation, so obviously you should be able to figure out the mole of the potassium chlorate. Because the question, what the question asking for? The question asking for what the mass of the potassium chlorate must have decomposed. Now you see, based on the stoichiometry, we can figure out from moles of oxygen to the moles of the potassium chlorate. And then we can base on moles of potassium chlorate to get the mass of the potassium chlorate. Does it make sense, right? So this is what you need to do. Then we go backwards. Based on the ideal gas law to figure out moles of the gas, and based on stoichiometry, figure out moles of potassium chlorate, and using the moles of potassium chlorate time molar mass, then you got the mass of the potassium chlorate. Make sense? Okay, yeah. So now first, let's just work on how to get moles of gases. So PV equal to nRT. So the N should be equal to PV divided by RT. So P is 0.9618 atmosphere. The time volume, 6.41 liter, divided by R, 0.08206, and time temperature, the temperature is 291.7 Kelvin. Okay, once you get figure out this, then you should be able to figure out what is the moles of oxygen. And by the way, make sure you have a parenthesis when you type this into the calculate. 0.9618 times 6.41 divided by parenthesis 0.0828206 times 291.7. And you got 0.2576. 0.2576, and this is a mole of the oxygen. Okay, now you know we have a 0.2576 mole of the oxygen, and then you can, based on the stoichiometry, to figure out moles of the potassium hydroxide, another potassium chlorate. Okay, so now what we do? Okay, now what we have a 0.2576 mole of the oxygen. And based on the stoichiometry, okay, again, how many moles of oxygen need to require how many moles of the potassium chlorate? Well, obviously, 3 moles of the oxygen need 2 moles of the potassium chlorate to be decomposed. Okay. So now you say mole of the oxygen is canceled. Now you got mole of the potassium chlorate. And then you can, based on mole of the potassium chlorate, and you time molar mass, you will figure out what is the mass of the potassium chlorate. So let's figure out what is the molar mass of the potassium chlorate. For the potassium, the 39 plus chlorine, that's 35.453 plus oxygen 16 times 3. So the molar mass of the potassium chlorate (39 plus 35.453 plus 16 times 3). Got a 122.453. Okay. 122.453. And remember, the molar mass is gram per 1 mole. 1 mole of the potassium chlorate has 122.453 gram. Okay, so now you multiply the molar mass. 1 mole of the potassium chlorate equal to 122.453 gram. Okay, so the moles of that and moles of that is canceled. Now you will figure out what is the mass of the potassium chlorate. .2576 times 2 times 122.453 divided by 3 times 1 parentheses. I got a 21.03. 21.03, and this is in gram. Okay, this is in gram. Okay, and then if you look at the question, the numbers the question gave, those are 3 sig fig. So the end, we should keep 3 sig fig for the answer. So the answer is 21.0 gram. 21.0 gram, and that's going to be the mass of the potassium chlorate. You see, this one is different from the first one. The first one, you're based on the stoichiometry, got the moles of oxygen, and based on the ideal gas law to figure out the volume of the gases. Okay, but this one is, okay, first you figure out the mole of the oxygen, and then you based on the moles of oxygen to figure out the mass of the potassium chlorate. Okay, so one is go forward, the other one is go backwards. Okay, Corey, do you have a question? Looks like you do have a question.
No, just soaking it in.
You're soaking it? Okay. All right, so let's take a break and then we will do some practice on it. Yeah. Okay, so now please work on the question number 5. This one has an equation, so you can just base on this equation for the star trigonometry. So let's go ahead to work on the question number 5, okay? And think about what we're gonna do. Is this going to using the ideal gas figure out the mole first and using mole to figure out the moles of others? Or first we do the stoichiometry and then we figure out something else. Logan, question number 5. Question number 5 to solve the problem.
Because here, this is 206.
Yeah, I know, but it's correctly right here. but it's yeah, I just put it there. Yeah, that's what I put on my items.
No, I'm talking about this is a 8206. There's a 0 between 2 and 6.
Oh, okay.
You could do that.
Okay, so let's work on this question. Okay. Is that okay if I erase this part? Okay, yeah. Okay, so now we have this equation and you see what we have. We have 18.2 gram of the copper 1 sulfide. Okay, and the question asking for the volume of the SO2 is not all oxygen. Okay, so that's why first, well, you probably need to figure out mole of the copper 1 sulfide. And then you figure out, okay, what is the mole of the SO2 based on the copper 1 sulfide? And then you based on PV equal to nRT to figure out the volume, right? The volume should be equal to nRT divided by P. Okay, so this is the steps. Okay, so let's just first figure out what is the moles of the SO2 based on the moles. Based on the mass of the copper 1 sulfide. So we have 18.2 gram of the copper 1 sulfide. And obviously you're gonna divide by molar mass to get the mole of the copper 1 sulfide. So if you look at the molar mass of the copper 1 sulfide, that's gonna be 63.546 times 2 and plus sulfate. Sulfur is 32. Okay. 63.546 times 2 plus 32. So 159.092. 159.092. And this is a gram of the sulfate per 1 mole. Remember, this is 1 mole of the copper to 1 sulfate. Don't look at the coefficient. It just directly divided by, because 1 mole of that equal to that much mass. Okay, not 2 moles that's equal to that much mass. Okay, and then you figure out moles of this, and based on the stoichiometry, you can figure out the moles of SO2. You see, 2 moles of the copper to copper 1 sulfide can form 2 mole of the SO2 gases. Okay, so this is what we got from the coefficient. They say 2 mole of this to produce 2 moles of that. Okay, then you can, based on the stoichiometry, 18.2 times 1 times 2 divided by parentheses. Remember, you're gonna have the parentheses to cover the bottom parts. 159.092 times 2. And then you got 0.1144, okay? 0.1144, and that is a mole of the SO2. Okay, so now we got a moles of SO2. We know the temperature, so let's make a list for those parameters. Moles of this is 0.1144 mole, and the temperature here is 237 Celsius. You see, this is Celsius, so you need to plus 273, and you got, this is 510 Kelvin. Okay, and then the atmosphere, the pressure is 10.7 atmosphere. Okay, and what else? Nothing. Okay, then you can just plug all the numbers up there. 0.1144 times 0.08206. Okay, remember there's a 0 in between 2 and 6. And the time 510 Kelvin, and divided by 10.7 atmosphere. And then that's going to be the result. 0.1144 times 0.08206 times 510 divided by 10.7. And you got 0.4474. Okay, 0.4474. And then if you want to keep the correct sig fig, and you look at 3 sig fig, 3 sig fig, 3 sig fig, so we should keep 0.447, and this is in liter. Okay, well, there's a little bit different. Probably it's because the molar mass you use. Okay, yeah. So if it's just a little bit of difference, then that's totally fine. Okay, totally fine. All right, so you see, this is how we do the stoichiometry. Not too hard, right? I mean, the key is mole. We gotta mole something to figure out the moles of others based on the chemical reactions. You look at the coefficient, okay? But we have a different way to find the moles. Okay, solution, that's need to using molarity time volume. You got the moles. Okay, gas, you have to using ideal gas law to find the moles. Mass, if you have the solid mass, then you have to using mass over molar mass. You got a mole, right? So 3 different ways to find a mole, and then using the mole, apply that into the chemical reactions to find the moles of other stuff. That's it. That's it. Okay. Yeah. So that is the major thing we talk about today for the gas stoichiometry. The next 2 parts is not that important, and it's actually is easy to understand. The first one is called Dalton's law of partial pressure. Okay, Dalton's law of partial pressure. No, partial. Dalton's law of partial pressure. I mean, this is talking about a mixture of gases. So everything we talked about before, doesn't matter is ideal gas law or gas law or something else. All the gas law we talk about is talking about the same pure gas, right? If we talk about CO2, then it's just a CO2, pure CO2, okay? I didn't talk about a mixture, but the Dalton's law of partial pressure is talking about a mixture. So for example, if we have a container over there, right? So this container is not just containing the CO2. They also have oxygen, right? Or even they containing like a hydrogen gases, or they have a CO gases. So we have a lot of the mixture of the gases over there. Then the point is, how can we determine the pressure of each of the gases inside of those chambers? This is the topic that we talk about, the partial pressure. The meaning of the partial pressure is compared to the total pressure of the mixture of the gases, right? So if you have the total pressure for this container, it's just talk about what is the pressure of the mixture gas, okay? So the total pressure is talking about the pressure of the mixture, pressure of mixtures, mixture of gases. So this is talking about the total pressure. But if you're talking about the pressure for a single gas in the chamber, in this mixture, and this is talking about the partial pressure, okay? So the partial pressure, this is talking about the pressure of a single gas in the mixture. Okay, so this is the difference between the total pressure and the partial pressure. Okay, so the partial pressure is just the pressure of the single gases compared to the mixture. Okay, the reason it's called the partial is because it's part of the pressure. It's not the total pressure, right? Yeah, if it's a pure gases, well, the partial pressure will be equal to the total pressure. But since we have a lot of gases there, so definitely the pressure of the single gases is not equal to the total pressure. That makes sense, right? Yeah. Okay, so generally the equation, naming the Dalton's law of partial pressure telling us two things. Okay, the first thing is telling us the total pressure. Total pressure in the future, I'm going to write just a P and a TOT. Okay, TOT means partial pressure, means total pressure. So why I write the TOT? One of my students talking about, okay, so this one looks like a face. Yeah, I say, yeah, looks like a face, and somebody cry. Okay, yeah. Okay, so the total pressure, I'm going to just write like this. Okay, and partial pressure, I'm going to write like just a P and write a certain of the gases. Like a partial pressure of the CO2 is just a PCO2. The partial pressure of the oxygen is just a P oxygen. And this is talking about the partial pressure of certain gases, okay? So the total pressure should be equal to the sum of the partial pressures, okay? The total pressure is equal to the sum of the partial pressure. So if we talk about this case has 4 gases over there, then the partial total pressure of this chamber is just equal to the partial pressure of the CO2 plus the partial pressure of the oxygen plus the partial pressure of the hydrogen and plus the partial pressure of the CO. Okay, so total pressure is equal to the sum of the partial pressure of each of the gases. That makes sense, right? Yeah, that makes sense, right? Okay, so this is the first concept for these gases. Okay, this is the first concept. Okay, which means if you know the gas, the total gas, and you know the other three partial pressure, you should be able to figure out the last pressure. That makes sense, right? Okay. The other two, the second topic for this is called the mole ratio of those gases is equal to the pressure ratios. Okay, what does that mean? They call it mole ratio is equal to the pressure ratio. Okay, so one of the example is over here, then that's okay. So if you know the mole of the oxygen, let's say for example, we have the four gases. If you know the mole of the oxygen, and if you're divided by the mole of the total moles, then this is what we call the mole ratio. Then that should be equal to the pressure ratios, which means it should be equal to the partial pressure of the oxygen divided by the total pressure of the mixture. Okay, so that is the same thing. The mole ratio will be equal to the pressure ratio. It's the same thing. Okay, mole ratio is equal to the pressure ratio. Or if you say, the mole of the oxygen, you're divided by mole of the CO2. Well, then they will also equal to the partial pressure of the oxygen divided by the partial pressure of the CO2. Okay, so generally the mole ratio should be equal to the pressure ratio. This is another topic we talk about here. Okay, this is another topic we talk about. Well, so if you're based on this, then you can figure out, okay, how do we figure out the mole ratio, the partial pressure of the gases? If we know the moles of each of the gases, then we can, based on the moles of the gases, to figure out the partial pressure of the gases. That makes sense, right? So you see, based on this equation, we can easily to figure out what is the partial pressure of the oxygen. Well, the partial pressure of the oxygen will be just equal to mole of the oxygen divided by mole of the total moles, and you multiply the partial pressure of the total pressure. You see, this is how we figure out the partial pressure of each of the mixtures, each of the single gases. If you know the mole ratio for this, and then you multiply the total pressure, you will get the partial pressure of these gases. Okay, yeah, so that is why the mole ratio is pretty important when we talk about this. Okay, as long as you can know the moles, and then you can figure out the partial pressure. So those are the two things that we talk about in the Dalton's law of partial pressure. The first one, total pressure is the sum of those each others. Okay, yeah, you add the partial pressure together, you will get the total pressure. Second one is the mole ratio of the gases should be equal to the pressure ratios. Okay, yeah, so let's just work on this. And just to let you know, some of this partial pressure is pretty complicated. I'm not going to talk about those complicated things. The partial pressure things, if you want to go deep, it will be very deep. Okay, yeah. So you can apply everything you learned in gas law in this situation, but I'm not going to talk about that's too deep, too much. Okay, this is not for the intro, the Chem 1. But if you want to solve some simple one, and that's you can solve. For example, number 4, you say a mixture of the 2.0 moles of hydrogen, 3 moles of the ammonia, 4 moles of the CO2, and 5 moles of the N2 exert a total pressure of 800 torr. So what is the partial pressure of each of gases? Well, you know the moles of each of the gases, and then you know the total pressure of those gases. And based on the mole ratio, and then you should be able to figure out the total pressure, the pressure for each, right? So then, you know, if we talk about the partial pressure of the hydrogen, well, then that should be equal to the mole ratio, which is the mole of the hydrogen divided by the total mole of the gases, and then you multiply the total pressure. Well, multiply the total pressure. So the hydrogen you have is a 2.00. Total moles, then you sum them together, 2 plus 3 plus 4 plus 5. So you get 9, 12, 14. So you divide by 14.00 and time total pressure. Total pressure is 800 torr. Well, then after the calculation, you will figure out what is the partial pressure of the hydrogen, right? So 2 times 800 divided by 14, you got a 114, okay, 114. So now you have 114 torr. That makes sense, right? Yeah, and then you can do exactly the same thing for the ammonia, CO2, and the nitrogen. Okay, let me just do one more. The partial pressure of the ammonia, that's just equal to mole of the ammonia and divided by total moles of the gases. And then you time the partial pressure under the total pressures. Then the moles of ammonia, that's a 3.00 divided by total, which is 14 moles. And you time the total pressure, which is 800. And then you will figure out 3 times 800 divided by 14. It's 171, okay? 171 torr. Okay, and then now I don't have to work on the rest of this, okay? So you can base on the same equation to figure out the rest of the other twos, right? So they're pretty straightforward. The mole ratio is equal to the pressure ratios. If you figure out the partial pressure of the gases, you got the mole ratio of this, you time total, then that's it. Okay, and then if you talk about the question number 5, it's doing the same thing, okay? The partial pressure of the F2 gases is 300 torr. And in a mixed gas where the total is 1 atmosphere, so they're asking for what is the mole fraction. The mole fraction is the same meaning for the mole ratio, okay? The mole fraction is the same meaning for the mole ratio. Well, then how do we figure out? Okay, obviously we talk about the mole ratio is just equal to the mass ratio, the partial pressure of the gases over the total pressure. That's it, right? But obviously you need to make sure the unit is the same. You cannot simply using 300 divided by 1. Okay, yeah, you need to make sure the unit is the same. Either you convert the 1 atmosphere to torr, or you convert the torr to atmosphere. Doesn't matter which one, but you have to make sure the units are the same. Okay, yeah. So to me, I just convert the 1 atmosphere to 760, and then you can using the mole fraction or the mole ratio for the fluorine gases then that's just equal to the 300 torr divided by 760 torr. $300 divided by 760, and you got 0.395. Okay, you got 0.395, and that is the fraction. I mean, for this one, there's no unit because you see, probably this is easier to look at. Okay, yeah. Otherwise, you. Okay, so the 300 torr divided by 760 torr, you got a number, and this number do not have a unit because you see torr and a torr, the unit are canceled. So there's no unit over here. Okay, yeah. So that is going to be called the mole fraction for this question. That makes sense, right? Makes sense. Okay, yeah. Again, mole ratio is equal to the pressure ratios. Okay, mole ratio is equal to the pressure ratios. The mole fraction is just the same, talk about the mole ratio. That's the same thing, okay? Okay, so this is the topic for the partial pressure for the Dalton's law of partial pressure. And then let's take a break and we will talk about the last concept.
If one person, that's $10,000, pretty close already. Usually that's the second one ever in World Series history. Michael stuff that. Last night. Just basically did that.
Okay, so the last topic we're going to talk is called Goldham's law. You see, Goldham's law and the diffusion of the gases. It just talk about the diffusion rate. And you can think about, do you have any idea what is the diffusion? Yeah, the gas spread out, but they spread, generally the diffusion is talk about, okay, so if we have a container like this, and the container has a lot of the gases, okay? And then if we has a certain switch open over there, oops. Okay, and then the gas is going to flee out, right? When they flee out, and then we talk about how fast the gas will flee out. It's not always the same, I mean, different gas, the flow rate or the diffusion rate is different, okay? Some of the gas can diffuse very fast. Some of the gas diffuse very slow. That's really depends on the mass of the gases. You can think about it, right? If you have the heavy gas, then can it move faster? No, right? So heavy gas usually moving very, very slow, okay? But the smaller, I mean, lighter gases, it will moving pretty fast, okay? So generally, the major concept, it just let you know, is heavy one moving slower, lighter one moving faster. So generally, this is the topic for the diffusion. Okay, so let me just show you one of the video. This guy has a pretty interesting accent.
Graham's law of diffusion of gases. Objective: to understand the basic principles of the diffusion of gases and Graham's law of diffusion. Gas molecules move from areas of higher concentration to areas of lower concentration in a process called diffusion. A Scottish chemist, Thomas Graham, proposed a law that states that the rate of diffusion of one gas through another is inversely proportional to the square root of the density of the gas. This came to be known as the Graham's law of diffusion of gases. This law can be mathematically represented as diffusion rate of a gas, R, is inversely proportional to the square root of its molar mass, m. For a mixture of two gases, this equation is given as R1 divided by R2 is equals to square root of m2 divided by m1. For example, consider two gases, ammonia and hydrogen chloride, and apply Graham's law. Then it gives R NH3 divided by R HCl is equals to square root of MHCl divided by MNH3. Molar mass of HCl is equals to 36.5 and molar mass of NH3 is equals to 17. Now substitute the values in the equation. Square root of 2.147 is equals to 1.465. This reveals that rate of diffusion of ammonia gas is 1.465 times to that of hydrogen chloride. In other words, ammonia gas will travel 1.465 times more than hydrogen chloride gas when they were allowed to diffuse. To study the diffusion pattern of two different gases, let's perform a simple experiment. We require ammonia and hydrogen chloride solutions, 2 small cotton balls, 50 centimeter glass tube open at both ends, and 2 rubber corks. Take a cotton ball and dip it in ammonia solution NH3. Dip another cotton ball in hydrogen chloride solution HCl. Place the 2 cotton balls in the glass tube at the 2 ends simultaneously and close the 2 ends of the tube with rubber corks. Inside the glass tube, gases from the 2 solutions will begin to move in the opposite directions to each other. After some time, ammonia gas and hydrogen chloride gas will meet and react to form a white solid ammonium chloride. Mark the point where the gases meet and form ammonium chloride. Measure the distance dNH3 from the ammonia end and dHCl from the hydrogen chloride end. Ammonia gas will travel a longer distance, 30 centimeters, while hydrogen chloride will travel a shorter distance, 20 centimeters. The diffusion rates of each gas will be the distance traveled by each gas. So, 30 divided by 20 is equals to 1.5. Now let's compare the theoretical value from Graham's law to 1.465 and practical value from the experiment is 1.5. It is experimentally proved that ammonia gas will travel faster than hydrogen chloride gas. In other words, lower molar mass gas will diffuse quickly than higher molar mass gas. Summary. Gas molecules will diffuse from areas of higher concentration to areas of lower concentration. Diffusion rate of a gas is inversely proportional to the square root of its molar mass. Ammonia gas will diffuse more quickly than hydrogen chloride gas.
Okay, so that is the for the diffusion. Okay, for this part, I don't want you to do the calculation for the equation like the square root, the rate, 2 rates equal to the invertly square root of the molar mass. But I want you to, conceptually understand. Heavier molar gas should travel slower, right? The lighter gas should be travel faster, which means the diffusion rate is faster. Okay, heavier gas diffusion rate is slower. Lighter gas diffusion rate is higher. That makes sense, right? Okay, so now the conceptually understand, then we have the sum of examples. Okay, we have a sum of the gases. Let's just see. Okay, we have CO, CO2, ammonia, okay, nitrogen, oxygen, and methane. So now we have those 6 gases, and the 6 gases try to attend the Olympic track, okay, track speed. So which one is going to, the running or diffuse fast, the fastest, the fast one? Which one will go fast? The lightest one. Which one is the lightest? Then what are you going to do? Then you count the molar mass, okay? And which one has the smallest molar mass? Then you need to calculate, right? Go ahead. then you can see, okay, so methane, 16 gram per mole. CO, 28 gram per mole. CO2, 44 gram per mole. Ammonia, 17 gram per mole. Nitrogen, 28 gram per mole. Oxygen, 32 gram per mole. Okay, so which one? Methane. So methane is the diffusion that's go fastest. And which one is go slowest? Well, then you just need to look at the heaviest the molecule, right? Heaviest is this guy. So this one is going slowest. That makes sense, right? So not too hard, right? The diffusion concept, this is the only thing that I want you to understand, okay? Yeah, heavier one goes slower. Lighter one go faster, that's it. Okay, yeah. So, okay, so now we're done for today's lectures. And then we can move to the lab and then we will work on the study guide.